Concrete is one of the most commonly used materials in the construction industry. However, it is very susceptible to cracks because cracks can cause a rebar corrosion, which leads to spalling and further cracks. So the aim of this project is to introduce sensing and healing technologies such that it is able to sense automatically when a crack occurs, as well as to undergo a first aid repair autonomously. Cracks in concrete are insidious because they are very small and very difficult to be detected by the naked eye. So the ability to be able to detect those cracks automatically will be very attractive to engineers. The corroded rebar can expand and cause further cracking and spalling of the concrete cover. The key challenges in this project is twofold. The first is the sensing technology. It must be sufficiently sensitive and it must be able to tell us where the crack locations are. The second is the healing technology. The healing must be able to be repeatable. In other words, when a crack occurs first time and it's healed, and then subsequently if there are more cracks, it is still able to heal it. One of the approaches we have adopted is the use of a smart conductive paint as crack sensors and an internal vascular system for delivery of healing and sealing agent. The vascular system comprises of tunnels prefabricated into the concrete specimen are located at the base of the concrete specimen, where cracks usually initiate and propagate. Cracks as small as 0.3 mm can be detected and sealed with our technology. Larger cracks can also be sealed as sufficient amount of healing agent could be delivered via pump. There are three other competing technologies. The first one is a bacteria-based healing system. Here, live bacteria are embedded into the concrete material, waiting for the right time when crack appears in the concrete. Then the bacteria will be activated to heal very tiny cracks. Second is the SAP, which is the super absorbent polymer. In this case, the super absorbent polymer is embedded in the concrete when a crack occurs, and while waiting for rain to come or for some external input of water by engineers, the SAP will grow and hopefully heal the crack. And lastly is the use of nanocapsules, which are also embedded in the concrete. These nanocapsules are small. In this case, they will only be able to heal very tiny cracks. One of the technical challenges is to select the most suitable sealing and healing agent, which could provide both sealing and healing properties. At the moment, we have experimented with cyanoacrylate-based glue, single-part epoxy, styrene butadiene, and testing is still in progress to select the most optimal healing agent. There are two significant advantages of this project that we're doing. The first one is the ability to sense. In the previous three competing technologies, they weren't able to sense crack at all. They merely heal those cracks. But in our project, we were able to have the sensing ability as well as the healing ability. This is an integrated approach to smart structures. The second significant advantage is the ability to heal much larger cracks compared to the three competing technologies that I've mentioned. Here we managed to heal cracks as big as 2 mm in crack width. For future work, we would like to experiment this in much larger structures as well as to implement them in field trials.